G'day boys and girls, welcome back to another episode of McGrathematics for the Extension 2 course. Starting off with a flashback from lesson 2 on polynomials, we've got if z equals 2 plus I is a root of this polynomial where a is a real number, what is the value of a? If you think you know how to solve it, please pause and have a go yourself before I run through my solution. Okay, one way we can handle this is we can just straight up substitute 2 plus I into our polynomial and set it equal to 0 since 2 plus I is a root. That'll give us an equation to solve for a, and it shouldn't be too tedious. However, subbing in 2 plus I and having to square it and cube it is a bit of room for error with some negatives floating around in the wrong spot. So I think it's maybe a little bit safer to answer this question using alpha, beta, and gamma using the sum and product of roots. So to start off with, I'm going to say we know one root is 2 plus I. We know thanks to the conjugate root theorem that 2 minus I is also a root. And then the third one is going to be gamma, which we can figure out pretty quickly using the product of roots. We can't use the sum of roots yet because we don't know what the coefficient of the z squared is. So starting off with the product of roots, alpha times beta times gamma. This is equal to minus d over a in any cubic polynomial. Now expanding 2 plus I and 2 minus I, we'll get 4 minus I squared. I squared, of course, being minus 1, so this gets us 5 gamma is equal to minus 15, because that is negative 15 divided by 1. Solving this, we get the third root of gamma being equal to minus 3. Now, of course, we could just sub minus 3 into the polynomial and figure out what a is. That wouldn't take too long. Or if you want, you can use the sum of roots and say alpha plus beta plus gamma is equal to minus b over a. The i's cancel out, and then 4 minus 3 is equal to 1. So we get 1 is equal to minus a, because that's negative. It's confusing, but b is a in this example, I know. Anyway, we get 1 is equal to negative a, therefore a is minus 1. So well done if you chose option A for your answer. Okay, beautiful. On to today's lesson, which is all about the roots of complex numbers. So kicking off with, we are going to find the fourth roots of minus 1 for our first example. So essentially what that means is we are trying to find a complex number z such that z to the power of 4 gets us an answer of minus 1. Okay, so we've done questions like this when we were finding square roots of complex numbers. We did that in our quadratic equations lesson. Today we're looking at a convenient way of finding higher powers like the power of 3, 4, 5, and onwards. Okay, here's our process. It's a few steps to it, and it does take some practice to get the hang of, but once you've got it down pat, you can confidently use this for any example. All right, first thing we're going to do is take our equation, which is z to the 4 equals minus 1. We're going to write both sides of that in polar form. So z to the power of 4, if we were using a generic complex number and wrote this in polar form, we would get r to the 4 cos 4 theta plus I sine 4 theta using de Moivre's theorem. Now over on the right, if you think of minus 1, it's to the left of the Argand diagram. It's 1 unit to the left, so we have a, what's it called again? A modulus of 1, and we have an argument of pi, because we're on the left-hand side of the axis. Okay, cool. Now comparing both sides of this equation, we can say, well, if r to the power of 4 is equal to 1, this tells us that r must be equal to 1. I know this equation does have plus or minus 1, but keep in mind that r is a modulus, it's a length, so we only take the positive value and we ignore the negative. So we know all of these roots of minus 1 are going to be length 1. We need to now find where they are by finding their angles. The way we do this is we say, well, the 4 theta must be equal to the pi, but then keep in mind that these two are going to be equivalent on the next lap around of the circle. So if we added 2 pi to this and maybe had 3 pi, this would be equal to 4 theta as well. Okay, so cos 4 theta plus I sine 4 theta is equal to cos pi plus I sine pi when the angle 4 theta is equal to pi or the next rotation around the circle. The way we write that is we're going to have pi plus 2 pi times k. Okay, so this could be pi plus 2 pi, it could be pi minus 2 pi, it could be pi plus 4 pi. You know, we're doing all the laps to get all the solutions because we need 4 solutions because we have 4 roots of minus 1. Hope that makes some sense. All right, so dividing both sides by 4 gets us the expression theta is equal to pi plus 2k pi divided by 4. Okay, the way we're going to get our 4 angles is just subbing in 4 values of k, where k is a whole number. Works best if you start with 0 and then do -1, +1, -2, +2, and so on until you have as many solutions as you need. So to get our first value for theta, we're going to sub in k equal to 0. So we get pi plus 0 over 4. So our first argument, our first angle, first location is pi on 4. Next one, subbing in -1. So we get pi minus 2k pi, pi minus 2 pi over 4. That gets us minus pi on 4. Next up, we'll sub in k equal to 1. And so we'll get pi plus 2 pi over 4. So we'll get 3 pi on 4. And then for the last one, if we use -2, we get an argument of minus 3 pi on 4. Okay, so notice that we have the conjugates of all of our angles. We have pi on 4 and minus pi on 4, 3 pi on 4 and minus 3 pi on 4. The reason for this is because what we were solving was essentially a polynomial which had all real coefficients. There's no imaginary numbers in this equation, which means that our solutions using the conjugate root theorem should all be conjugates, which is why we are seeing plus and minus on our angles. Okay, so keep in mind, conjugate root theorem still applies even if it's a basic polynomial. Okay, so here are our 4 solutions. So now let's write our answers in polar form. So we have all of our moduli being 1 as we found, and our arguments are pi on 4, minus pi on 4, 3 pi on 4, and minus 3 pi on 4. If we had a look at these on an argand diagram, what you would notice is that of course they all have the same length, and your 4 roots are always going to be equally spaced around the argand diagram. That can make it useful because if you know where one of the roots are, you can pretty quickly figure out where the other 3 are because you know they're going to be evenly spaced out. So all the examples today we're going to see where we're finding roots of complex numbers, the answers will always be evenly spaced around the argand diagram and they will all be the same distance from the center. So please be aware of that. Okay, let's do another example to build some more confidence with this new idea. This time we're finding the complex cube roots of the complex number root 3 plus I. Okay, what that means is we are essentially trying to find a value of z such that z cubed is equal to root 3 plus I. Our process for this is going to be the same as what we did in the last example. We're going to write both sides of the equation in polar form. We're going to compare and solve, and we're going to be looking for 3 distinct solutions. Okay, so first step, writing the left-hand side in polar form. You can use the shorthand if you prefer. So we have r cubed cos I sine 3 theta. On the right, in polar form, root 3 plus I is equal to 2 cos I sine pi on 6. Now, comparing both sides, we'll say r cubed is equal to 2, which gets us that r must be equal to the cube root of 2. Now we'll say our angle, 3 theta, must be equal to pi on 6, or it could be pi on 6 plus or minus multiples of 2 pi, going around that unit circle. So the way we write that again is 3 theta is equal to pi on 6 plus 2k pi, where k is an integer. Tidying up the right-hand side, we divide them by 3, so we get pi on 18 plus 2k pi on 3. All right, now substituting in values of k, starting off with 0. So when k is 0, we get just pi on 18. So there is our first location, pi on 18. Now if we make k equal to minus 1 and substitute in here, pi on 18, take away 2 pi on 3, will get us negative 11 pi on 18 for our second solution. Now if we let k equal to 1, we get pi on 18 plus 2 pi over 3, which gets us 13 pi on 18. So these 3 angles are evenly spaced around the argand diagram. However, this time they are not the conjugates of each other because the complex number we were looking at, so the equation we were solving, had an imaginary coefficient. Okay, last time it was just numbers. That's why we had the conjugate root theorem and we had conjugate answers. This time, because we have an imaginary part to our complex number, we're not going to see conjugates in our roots. Okay, writing our answers in polar form, we have, once again, all moduli of cube root of 2, and our 3 values for our arguments. Okay, if you sketched them, you would see they are evenly spaced around the argand diagram. All right, beautiful. If that's making sense to you, now is a chance for you to try one by yourself and see if you can work through the process and get your 3 answers for the complex cube roots of I. If you're still feeling a bit weird and you want to see me go through another one, that's what I'm about to do. So let's jump in. All right, starting off with our equation, z cubed equal to I. That's what we're trying to solve. We're trying to find z values for this. Writing both sides in polar form, we have r cubed cos I sine 3 theta equal to, so I is just straight up on the argand diagram. So it's a length of 1 and an angle of 90 degrees, or pi on 2. Okay, comparing, we get r cubed is 1. This means that r must be equal to 1. We get 3 theta is equal to pi on 2 plus 2k pi, okay, because once again, could be plus multiples of 2 pi. Dividing everything by 3, combining these two fractions, or these two terms, we get pi plus 4k pi over 2, divided by 3, and we get pi plus 4k pi over 6. Doesn't really matter how much you simplify the right-hand side, as long as you have the correct expression, we're going to get the same answers when we sub in values of k. So if yours doesn't look exactly like this, don't freak out, we'll probably get the same answers anyway. Okay, so we have our moduli, we just need our arguments, and we need 3 of them, so we're going to substitute in 3 values of k. We're going to start with 0, then we'll do -1, and then we'll do +1. Okay, so when k is 0, we get just pi plus 0 over 6, so we get pi on 6. The next one, when we are equal to k being -1, we get pi minus 4 pi, which is -3 pi on 6, which simplifies to minus pi on 2. Okay, up next we have k equal to 1, so we have pi plus 4k pi, plus 4 pi, so we have 5 pi on 6. Once again, not conjugates because we have an imaginary term in our equation, but they are evenly spaced out, and so there are our 3 answers. Well done if you got the same thing before me and you're already getting it. Okay, one last example on finding complex roots before we move on to the second half of this lesson. So fourth example, we're going to be solving for z as a part of the, that should not say z, that should say c for complex. So apologies for that. We're trying to find complex numbers, z, such that z to the power of 6 plus 64 is equal to 0. Once again, dive in and have a go if you think you know what you're doing. Okay, first things first, I'm going to move the 64 across the right-hand side. So now I'm trying to find the 6th roots of minus 64. Okay, let's start by writing both sides in polar form. So we have r to the 6 cos I sine 6 theta. Over on the right, minus 64 is 64 units to the left of the Argand diagram. So we have a length of 64 and an angle of pi. Okay, if r to the 6 is 64, that should say 64, not 1. This is going really well. That means that r is equal to 2. So just change that to a 64, please. Should I edit this? Can I be bothered? No, I can't. All right. Now, 6 theta is going to be equal to pi plus multiples of 2 pi. So we write 6 theta equals pi plus 2k pi, where k is an integer. Rearranging this, we have dividing by 6. We got pi plus 2k pi divided by 6. Now we have an expression we can substitute in some values of k. We're trying to get 6 distinct answers because we have 6 roots of minus 64. All right, our first one, subbing in k equals 0, we get pi on 6. For the second one, subbing in -1, we get minus pi on 6. Okay, this time, once again, we are seeing conjugates because our equation, as we notice, is all real numbers and no imaginary constants. Okay, when theta is equal to 1, we end up with 3 pi over 6, which we'll write as pi on 2, which means the next one is probably going to be minus pi on 2 because we are expecting conjugates. Okay, next up, we'll make k equal to 2, so we'll get 5 pi on 6. And then our last one, when k is equal to -3, we of course get minus 5 pi on 6 as the conjugate of the number above. All right, groovy. We have all of our moduli being 2. We have our 6 arguments, so now we can write our answers in polar form. And here are the 6 roots of minus 64. So these are the 6 numbers which solve this equation. All right, lovely. Let's move on to the second half of today's video. Okay, up next we are talking about the roots of unity, okay? So roots of unity is just another way of saying the complex roots of 1. Okay, for example, if we were finding the 4th roots of unity, that's just a fancy way of saying, hey, solve the equation z to the power of 4 equals 1, okay? Find me the 4 complex numbers that when I raise them to the power of 4, I get 1 as an answer. Okay, so when you see unity, please just think 1. Okay, here's what they're going to look like on an Argand diagram. We know that 1 is obviously an answer because 1 to the power of 4 is equal to 1. So there's your real answer. We'll have some other ones which may be complex or real. We can find them pretty easily because we know they're all going to have the same modulus and we know they're going to be evenly spaced around the Argand diagram. So we know we're going to have 1i, -1, and -i. Let's see how we could have got that result algebraically using a bit of cheeky factorization. So pulling the 1 across the left-hand side, we can factorize z to the 4 minus 1 as a difference of squares by having z squared minus 1 and z squared plus 1. Now, z squared minus 1 we can easily factorize since year 9. Z squared plus 1 we can factorize by being a bit cheeky and writing the plus 1 as a minus I squared. So difference of squares on the left, and now we have a difference of squares in the second half. So we get minus I and plus I. There we can see our 4 answers for our fourth roots of unity are 1, minus 1, I, and minus I, as we are seeing from the Argand diagram. Okay, so some things to be aware of. The roots of unity will always include equal 1, as we're seeing here. Okay, which makes, whoa, what's that? Which makes finding them a lot easier because you know you're always going to have 1, and you know they're always going to be evenly spaced around, so you can pretty quickly draw a good sketch of what your roots of unity look like, which should help you find your answers relatively quickly. Okay, always includes 1, evenly spaced around the Argand diagram, so whatever power you are finding, if you divide 2 pi by that power, that will tell you how far apart they are. Okay, and because roots of unity will be equations with no imaginary terms, we have only real numbers, which means the conjugate root theorem will apply. So we'll always see conjugate pairs. So if omega is a root of unity, then omega conjugate is also a root of unity, which makes finding them even easier again. Okay, a very useful factorization that is going to be very helpful for the examples today. So you know how to factorize a squared minus 1. You've been doing that since you're a baby. Difference of squares, a minus 1, a plus 1. Now, in the old advanced maths course, we used to teach you how to factorize what's called a difference of cubes. For some reason, we don't anymore, so I'm going to do the quick version for you. A cubed minus 1 can be factorized to a minus 1, a squared plus a plus 1. Okay, now when I show you the next one, a to the power of 4 minus 1, you're going to see a pattern. The factorization of a to the 4 minus 1 is a minus 1, a cubed plus a squared plus a plus 1. So hopefully what you're seeing is that the front term is always a minus 1, and then the second term in brackets is always 1 power less than what we started with, and stepping down in powers all the way down to 1. So if we had a generic version of a to the n minus 1, the factorization of this could be a minus 1, and then a to the 1 less, plus a to the 2 less, plus etc., all the way down to a plus 1. Okay, this is really useful because this is what our equations look like when we're solving roots of unity, because we have a power equal to 1. If you bring it across, you have minus 1, and you can apply this technique to factorize pretty quickly and use some algebraic results, which you'll see shortly. Okay, let's dive into an example. So we have omega is a complex cube root of unity. First part, show that 1 plus omega squared is equal to 0. Okay, so to work with this one, first of all, if omega is a complex cube root of unity, it means that omega cubed is equal to 1. Okay, that's the definition of a root of unity. Now, if we pull that 1 across the left-hand side, we have omega cubed minus 1 equals 0. Using that technique I just showed you, we can now factorize this as omega minus 1, and then omega squared plus omega plus 1 equal to 0. So the real cube root of unity is obviously going to be 1 if we solve the bracket at the front equal to 0. But because the question said omega is a complex cube root of unity, it must be coming from this second bracket here, which tells us that it's an omega. Omega squared plus omega plus 1 is equal to 0, which is essentially what we were asked to show in part A. So that's how we do it. So just setting up your equation, factorizing, and then solving equal to 0 using the complex part and ignoring the real part. Okay, for the next part, we're showing that 1 plus omega conjugate is equal to 0. Okay, what we have here are essentially our 3 cube roots of unity. We have 1, which we know is an answer. We have omega, and we know that if omega is a root, then so is omega conjugate. All right, so since omega is a cube root of the polynomial, it means that it's a solution of z cubed equal to 1. All right, if we factorize, so if we pull it over to the left-hand side, we have a polynomial. And now because we have a polynomial with real coefficients, we can say, well, if omega is a root, then that means that omega conjugate is also a root, thanks to the conjugate root theorem. So we've established that 1, omega, and omega conjugate are our 3 roots. So if we were adding them together, we would essentially be doing the sum of the roots of this cubic polynomial. which is something we have quite a lot of experience with. We know that if we add the three roots of a cubic polynomial, we get a result of minus b over a. Now in this polynomial, our value of b and c is both 0. So if we did minus b over a, we would get negative 0 over 1. We'll get an answer of 0, and that was the result to prove. Okay, so part B is really just saying, hey, take the sum of the roots and show that's equal to 0 using minus b over a. Okay, question C and D is where it gets fun. Now we start to do some interesting algebra. So let's have a look at question C. All right, so we got 6w plus 1 multiplied by 6w squared plus 1. If we expand this whole thing out, we get 36 omega cubed. Sorry, I keep saying w, it's an old habit, I'm stupid. We get 6 omega squared, we get 6 omega, and we get plus 1 on the end. What we can do now is separate this, so we know that of course omega cubed is equal to 1 because omega is a complex cube root of unity. Okay, so omega cubed is 1. Now we're going to write this plus 1 in a really clever way. Because we have a 6 omega squared and a 6 omega, it'd be really good if we had a 6 here. So that's what we're going to do. We're going to write this as 6 take away 5. Okay, that's a clever way of writing 1 because now we can factor a 6 out of these three terms in the middle. So we have 36 times 1 plus 6 times omega squared plus omega plus 1 take away 5. We know from part A that omega squared plus omega plus 1 is equal to 0. So we have 36 plus 6 times 0 take away 5. So we have 31, which was the target to prove. So we have shown that the left-hand side is equal to the right-hand side. Okay, for part D, we are once again going to be doing some more clever algebra. So starting off with the 1 plus w squared. To get an expression for this, we're going to look at the result from part A, where we said 1 plus w, or omega, whatever, plus omega squared is equal to 0. That means that 1 plus omega squared could be written as minus omega if we pull this term across to the right-hand side. That's what we're going to do first, okay? We're taking the result from part A, moving the omega across the right-hand side. So we have 1 plus omega squared is equal to minus omega. That means the inside of this bracket, which is being cubed, we can just write this as a negative omega to make the algebra a bit more tidy. Now for our 2 plus 3 omega plus 3 omega squared, we're once again going to write our answer in a clever way. We're going to write this 2 as a 3 take away 1. We've done this, so once again we can factor a 3 out of these three terms. So we have a 1 plus omega squared. The reason for this is because once again, using the result from part A, we know that 1 plus omega squared is equal to 0. So this here is really 3 times 0 take away 1, which is just minus 1. Okay, so the first bracket is just going to be written as minus omega, and the second bracket can just be written as minus 1. So we have the left-hand side being negative omega to the power of 3 multiplied by negative 1. Now, negative omega cubed is negative omega cubed. Because we know omega is a cube root of unity, that means that omega cubed is equal to 1. So we have minus 1 multiplied by minus 1, and this gets us our result on the right-hand side of positive 1. Okay, so for questions like C and D, it's just a lot of clever algebra. It does take it takes a while to get the hang of it, but once you do, I think they're really fun questions. So dive in and have a go. Let's do a couple more examples before we call it a day. Okay, up next we have omega being a non-real 7th root of unity. We want to show that for part A, omega to the 8 take away omega is equal to 0. Okay, well, if omega is a non-real 7th root of unity, it means that omega to the power of 7 is equal to 1. We can pull the 1 across the left-hand side and have omega to the 7, take away 1 equals 0. Now to get our result, we can just multiply both sides by omega, and we have omega to the 8, take away omega equals 0 as required. Okay, for part B, we're trying to show that omega plus squared plus etc. up to the power of 6 is equal to minus 1. Okay, we're going to do a similar approach to part A from the last question. We're going to set up our equation for omega being a 7th root of unity. Now, whenever you see all these sums of powers leading up, this tells you need to bring the 1 across and use your factorization technique to get an equation. So pulling the 1 across and using our factorization technique, we can write the left-hand side as omega take away 1, and then omega to the 6, all the way down to omega plus 1. Now, since omega is non-real, we know it's not equal to 1, so we can scrap the bracket at the front, and we can say, well, this means that these all together are equal to 0. We can put the 1 across, and we get the -1, which is what we were trying to show for part B. Okay, beautiful. Up for part C, we have hence, show that the quadratic equation z squared plus z plus 2 has roots of alpha and beta given by these expressions. All right, cool. So what this means for part C is that if these are indeed the roots of this quadratic equation, it means that if we added them, we should get negative b over a. So we should get -1 over 1. So if we can show that these two add together and give us -1, we're on the right track. Then we need to show that the product of the roots, alpha, beta, is equal to c over a, which is going to be 2 over 1. So our goal for this question is show that alpha plus beta is -1 and show that alpha times beta is equal to 2. Let's see how we go. Let's start with the sum of the roots. Alpha plus beta. Well, if we add these all together, we're going to get omega plus omega squared plus omega cubed, all the way up to omega to the power of 6. Fortunately, in part A, we already proved that this is, sorry, in part B, I think, we already proved that this is equal to -1. And -1 is conveniently -1 divided by 1. So we have shown that the sum of the roots in this quadratic equation is equal to -b over a. So the first part is done. Now we need to show the same thing works for the product of alpha times beta. All right, so we're going to do a lot of expanding here. Alpha times beta is going to be a big trinomial expansion. So let's just dive in. If we work the whole thing out, we get to the 4, 6, 7, 5, 7, 8, 7, 9, and 10. Now we are trying to simplify this and show that we can make it equal to 2 because that's what c over a is for this quadratic. Okay, things to keep in mind that because omega is a 7th root of unity, wherever we see an omega to the 7, we can just replace this with a 1 because omega to the 7 is equal to 1. Extending upon that, that means that omega to the power of 8, this is omega to the power of 7 times omega. So we can just write omega to the 8 as just omega to the power of 1. It's going to repeat its cycle every 7 powers. Likewise, we can write omega to the 9 as omega squared, and we can write omega to the 10 as omega to the power of 3. So working that out, we've got 4, 6, we've got a 1 here, power of 5, 1, power of 1, 1, power of 2, and then power of 3. If we rewrite this in ascending orders, we have power of 1 all the way up to power of 6, and then the 3 ones together make a 3. Now, once again, from part B, we know that omega to the 1, summing with omega all the way up to the power of 6, this was equal to -1. So we have -1 plus 3. This is equal to 2, which is what we were trying to show, because 2 in this polynomial, this quadratic, is c divided by a. So there you go. We have shown that alpha and beta for this quadratic are the sum of roots and the product of roots. So it works. Hooray! Okay, example 3. We have omega being a non-real cube root, a non-real 5th root of 1. So it's a 5th root of unity. Part A we're going to skip because I think you guys can handle that by yourself. It's very similar to the questions from the last example. It's just setting up your equation, factorizing, and getting this result. We're going to skip straight to part B, which is the more interesting part of this example. We have hence, show that cos 2 pi on 5 plus cos 4 pi on 5 is equal to -1/2. All right, let's think about what our 5th roots of unity look like, because we're going to need to actually figure out what they are instead of just doing some algebra. So let's have a look at our picture. Okay, here are our 5th roots of unity. We of course have 1. Okay, 1 is always a root of unity. And the other 4 are going to be evenly spaced around the Argand diagram. So our 2 pi radians is going to be divided into 5 sections. So these are all going to be 2 pi on 5 radians apart. So we'll have 2 pi on 5 here, 4 pi on 5 here, and then we have our conjugates of -4 pi on 5 and -2 pi on 5. Okay, so here are our 5 5th roots of unity, just written in polar form. Now, this is the result that we're trying to prove. We need to add them together at some stage. So something to be aware of is a reminder of what happens when you add a complex number to its conjugate when it's in polar form. To show you what I mean, if we were doing cos I sine of 2 pi on 5, and we were adding to this cos I sine of minus 2 pi on 5. It would look like this. Okay, here's our 2 pi on 5s, here's our minus 2 pi on 5s. Now, a useful result we can use is that cos is an even function, so cos of minus 2 pi on 5 is equal to cos of positive 2 pi on 5. So we can ignore this negative here. We also know that sine is an odd function, so the negative inside of our 2 pi on 5 can be pulled out the front, and we can write this as minus I sine 2 pi on 5. Okay, this is good because our two sine terms are equal in magnitude but opposite in sign, so they cancel out, and our two cos terms add together and give us 2 cos 2 pi on 5. Okay, so if we added these two solutions together, our answer would be 2 cos 2 pi on 5. Likewise, if we added cos I sine 4 pi on 5 and cos I sine minus 4 pi on 5, our answer, or our simplified version, would be 2 times cos 4 pi on 5. All right, this is great because now when we add all of our roots together, we are summing the 5 roots of this polynomial right here. Okay, so we have 1 plus, adding all these values in red together. This will be equal to minus b on a. Now, in our polynomial, our value of b is equal to 0 because there's no power of 4. So this is going to be equal to just 0. Like I said, our conjugates adding together gives us this result which we looked at before. Now we're almost there. All we need to do is take the 1 across to the right-hand side to make it minus 1. And then we'll divide by 2 and we'll finish the question. Okay, so I've run out of space here, sorry guys, but the 1 goes across to become minus 1. Divide by 2 and you get the result which was required to be shown. Okay, and to finish off this lengthy video, we have a HSC question from 2021. It was a band 4. It was an interesting one. They gave you a diagram in your writing booklet and they said, hey, right here is the complex number a plus ib. For 2 marks, we want you to draw 4 dots showing the locations of the 4th roots of a plus ib. If you think you know how to handle this one, by all means pause and have a go. Otherwise, here comes the spoiler. All right, so first of all, we know that the magnitude or the modulus of our complex number a plus ib is greater than 1. This is important because we know that when we take the 4th root of this number, it's going to be a number smaller than what it is now, okay? Imagine this is like 1.3. If you did the 4th root of that, you would be closer to 1, but you wouldn't be on 1, okay? All right, here is where I know the first of our 4th roots are. The reason I know it's here is because imagine if I did this complex number to the power of 4. When you multiply complex numbers, their arguments add together. So power of 1, power of 2, power of 3, power of 4. Okay, this is a number where it could be like 1.1, 1.2. If I did it to the power of 4, it would be reasonable to get it up to this length here of whatever it is. Okay, it doesn't have to be exact. You just need to show that your modulus is decreasing, but it's not going to 1. It's going between 1 and where we originally started. Okay, once you get that one, it's pretty easy because you should know that your 4 roots are equally spaced around the Argand diagram, which means they are all going to be separated by 90 degrees. So I can put my second one up here, my third one 90 degrees along, and there is my 4th one. Okay, so here are the 4 locations of the 4th roots of this complex number. Okay, beautiful. That's it for today's lesson. Thank you for watching. Hopefully some of that made some sense to you. If you need any further clarification, that's what the comments are for. And I'll catch you guys in the next video. Here are some assigned exercises for my class. For everybody else, I'll hopefully see you next week. Bye for now. Cheers.